Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us into the night sky, where we will explore stars, planets, constellations, moonlight, meteors, and the quiet patterns that have guided human curiosity for thousands of years. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. Looking upward after sunset opens a view into both nearby space and deep cosmic history. At first glance, the closest bright object may be the moon, while the stars behind it are far beyond the solar system. Some of their light has crossed space for years, centuries, or far longer before entering the eye. This means the sky is not a single surface, but a layered scene with many distances stacked together. The dark spaces between stars are not empty in every direction. They contain faint gas, dust, galaxies, and objects too dim to see without instruments. To human eyes, the sky looks calm and still, yet it holds motion on every scale. Earth is turning, planets are orbiting, stars are moving through the galaxy, and light is always arriving from older moments. Much of the sky's apparent nightly motion comes from Earth's rotation. Stars seem to rise in the east and set in the west because the planet turns beneath them once each day. This steady turning creates the gentle sweep of constellations across the hours of darkness. Near the poles, some stars trace circles around the sky and may never set from that location. Near the equator, stars climb and sink more steeply, giving observers access to parts of both northern and southern skies. The movement is slow enough to feel almost still, but long exposure photographs reveal it clearly as graceful arcs. This daily pattern helped people measure time long before clocks became precise. The sky's calm drift is really the ground beneath us, carrying every observer eastward together. Night begins because the sun has slipped below the horizon. During the day, sunlight scatters through the atmosphere and fills the sky with blue brightness. After sunset, the sun's direct light no longer reaches the ground, so the stars and planets can stand out against a darker background. Twilight remains for a while because sunlight still touches the upper air above us. As the sun sinks farther below the horizon, the sky deepens from pale blue to dark blue, and then to black. The night is never perfectly black from the ground, because airglow, moonlight, starlight, and human lights can brighten it. Still, the change from day to night reveals objects that were present all along, silently waiting behind the daylight all afternoon, unseen overhead. Earth's atmosphere both protects life and slightly reshapes the stars we see. Starlight passes through layers of moving air before reaching the ground, and those layers bend and disturb the light in small ways. This is why stars often appear to twinkle, especially when they are close to the horizon. Their light has crossed more air at that low angle, so the tiny changes become easier to notice. Planets usually twinkle less because they show a small disk to our eyes and telescopes rather than a single point of light. The atmosphere can soften details, blur fine edges, and make objects shimmer. At the same time, it shields the surface from much harmful radiation and burns up many small incoming particles. The same air that makes stars waver gently helps make stargazing possible. Stars are suns so far away that most appear as tiny points of light. Each visible star is a glowing sphere of hot gas, powered by nuclear fusion in its core. The stars in the night sky vary widely in size, temperature, brightness, and age. Some are smaller and cooler than the sun, while others are far larger and much more luminous. Their distance makes them look delicate. even though many are powerful beyond ordinary imagination. To the unaided eye, a star does not reveal its round shape, because it is too far away for its disk to be resolved. What reaches us is a concentrated spark of light. This simple point can represent a world-sized object, a giant star, or part of a wider stellar family, all reduced by distance to a calm glimmer. Star color gives broad clues about surface temperature. Blue-white stars are generally hotter at the surface than yellow, orange, or red stars. The difference can be subtle to the eye, especially under bright skies, but it becomes clearer through binoculars, telescopes, or careful photographs. Betelgeuse in Orion has a warm orange-red cast, while Rigel in the same constellation shines more blue-white. These colors do not work like painted colors on a solid surface. They come from the balance of light given off by hot gas. A star's color is one of the first clues astronomers use when learning what kind of star it is. In a dark sky, the stars are not all plain white. They form a faint natural palette, spread softly across the darkness overhead. A star's apparent brightness depends on both true luminosity and distance. A star may look bright because it gives off a great deal of light, because it is relatively nearby, or because of both reasons together. Sirius, the brightest star after dark, appears so strong partly because it is close to Earth compared with many visible stars. Other stars that look faint may be far more luminous than Sirius, but they lie much farther away. Astronomers separate apparent brightness, which is how bright an object looks from Earth, from absolute brightness, which describes how luminous it would appear at a standard distance. This distinction helps turn the sky from a flat-looking pattern into a map of depth. A tiny faint point may hide an enormous star across a vast distance. With the eye alone, we see only a small fraction of the Milky Way stars. Under excellent dark skies, a person may see a few thousand stars at one time, depending on eyesight and local conditions. The Milky Way galaxy contains far more, on the order of hundreds of billions. Most are too distant, too dim, or too hidden by dust to stand out individually from Earth. The visible stars are like nearby lanterns on the edge of a much larger city. Telescopes reveal many more, and long exposure images reveal even fainter layers. The number of stars is not evenly spread across the sky, because we are looking from inside a flattened galaxy. Where our line of sight passes through denser parts of the galactic disk, the background becomes rich and softly crowded. From within our galaxy, the Milky Way appears as a pale band. It is not a cloud in Earth's atmosphere, but the combined glow of countless distant stars mixed with dark lanes of dust. From a truly dark location, the band can stretch across the sky like a soft river of light. Its brightest regions are seen toward the galaxy's central direction, where stars are more densely gathered. Dust clouds block parts of that glow, creating uneven shapes and shadowy gaps. The name Milky Way comes from its pale, spilled appearance to the naked eye. Modern astronomy shows that this misty band is the broad disk of our home galaxy, seen edge-on from our position inside it. What seems faint overhead is the structure that contains the sun itself. Constellations are human-made patterns drawn between unrelated stars. The stars in a constellation may look close together on the sky, but they often sit at very different distances from Earth. A pattern such as Orion or Ursa Major is a line-of-sight arrangement, not a cluster of stars physically grouped in space. Different cultures have drawn different figures in the same sky, shaped by their landscapes, stories, seasons, and needs. Modern astronomy uses official constellation boundaries to divide the entire sky into regions, rather than only the familiar picture shapes. This gives astronomers a shared way to describe where objects appear. The constellations are useful, memorable, and beautiful, but they are not fixed drawings placed in space. They are a calm meeting between human imagination and the real positions of stars. Known as an asterism, the Big Dipper is not a full constellation by itself. An asterism is a recognizable star pattern that may be part of one constellation or may cross between several. The Big Dipper forms the bright body and tail of Ursa Major, the Great Bear. Its 7 main stars are among the easiest patterns to find in the northern sky, especially from mid-northern latitudes. 2 stars at the outer edge of the bowl are often called pointer stars because they guide the eye toward Polaris, the North Star. The pattern changes position through the night and through the seasons, circling around the northern sky for many observers. Its familiar shape has made it a practical guide for direction and a lasting feature of sky stories. Simple patterns can carry a great deal of meaning. Polaris is useful for navigation because it sits close to the North Celestial Pole. This point marks the direction in the sky that Earth's northern axis points toward. As Earth rotates, most northern stars appear to circle around this pole, while Polaris stays nearly fixed in place. It is not the brightest star in the sky, despite its fame, but its position makes it especially helpful. In the northern hemisphere, the height of Polaris above the horizon is close to the observer's latitude. This gave travelers a simple way to estimate how far north they were. Polaris is only near the pole by chance in the present era. Earth's axis slowly wobbles over thousands of years, so other stars have served and will serve as pole stars in different ages. Because it is close to Earth and reflects sunlight, the Moon is the brightest natural object seen after dark. It does not shine by making its own light. Its surface sends sunlight back toward us, with the bright portion changing shape as the Moon orbits Earth. Although the Moon is much smaller than the Sun, it appears nearly the same width in the sky because it is far closer. This apparent size makes solar eclipses possible when the Moon lines up just right. The lunar surface is not smooth, even though it can look soft from a distance. It is covered with craters, plains, mountains, and fine dust. Its steady presence gives the night sky a changing center, from a thin crescent to a full round face above us. As the Moon orbits Earth, changing viewing angles create its phases. Half of the Moon is always lit by the Sun, except during a lunar eclipse, but from Earth, we see different portions of that sunlit half. A crescent appears when most of the lit side faces away from us. A full moon appears when the lit side faces Earth almost directly. The cycle from one new moon to the following new moon takes about 29.5 days. This rhythm helped many cultures build calendars, mark seasons, and organize ceremonies or work. The same moon keeps the same general face toward Earth because its rotation is locked to its orbit. Its phases are not shadows from Earth, but a graceful result of sunlight, motion, and perspective. Broad dark patches on the moon are plains called Maria. The word comes from an old Latin term for seas, because early observers thought these smooth areas might be bodies of water. They are not seas. They are ancient volcanic plains, formed when lava filled large impact basins long ago and later cooled into darker rock. The Maria are easier to see with the unaided eye than many smaller features. which is why people have imagined faces, animals, or figures in them. They are more common on the side of the moon facing Earth than on the far side. Their dark tone contrasts with the brighter, older highlands. These familiar markings make the moon recognizable from night to night and preserve a record of impacts and volcanic activity from deep lunar history. Craters on the moon remain noticeable for ages because the moon has little weather. On Earth, wind, water, ice, and shifting crust can soften or erase impact marks over time. The moon has no thick atmosphere, no rivers, and no rain to wear its surface down in the same way. When objects strike the moon, they can leave circular scars that persist for millions or even billions of years. Later impacts may overlap them, and tiny particles may slowly garden the surface, but change is slow. Through binoculars, some craters show bright rims and shadowed floors, especially near the line between lunar day and night. Those shadows reveal depth and shape with soft clarity. The moon's cratered face is a visible archive of collisions that shaped the early solar system. Planets can be recognized because they usually shine with steadier light and slowly shift against the stars. The word planet comes from an ancient idea of wandering stars, because these bright objects change position from night to night. Unlike stars, planets are nearby worlds in our own solar system, lit mostly by reflected sunlight. Mercury, Venus, Mars, Jupiter, and Saturn are visible without optical aid under the right conditions. They follow a broad path across the sky because the solar system is fairly flat, and Earth sees the planets near the same band where the Sun and Moon travel. Their positions change as Earth and the other planets orbit the Sun. A bright planet can look like a star at first glance, yet its slow wandering reveals that it belongs much closer to home. Venus is often the brightest planet because thick clouds reflect sunlight strongly. It can appear in the evening after sunset or in the morning before sunrise, depending on where it is in its orbit. For this reason, it has often been called the evening star or morning star, although it is a planet, not a star. Venus never appears far from the Sun in our sky because its orbit lies inside Earth's orbit. Through a telescope, it shows phases like the Moon, changing from a small round-looking disk to a larger crescent as its position changes. Its beauty from Earth comes from brilliant reflected light, while its actual surface is hidden below a dense atmosphere. In the night sky, Venus is a bright reminder that appearances can be simple and complex at once. Mars often looks reddish because iron-rich dust and rock cover much of its surface. The color is usually soft rather than fiery, but it can stand out beside whiter or bluer stars. Mars changes brightness dramatically as Earth and Mars move around the Sun. When the two planets pass relatively close, Mars can become one of the most noticeable objects after dark. At other times, it fades into a modest point. Telescopes have revealed polar caps, darker surface markings, dust storms, volcanoes, canyons, and dry landscapes shaped by a long history of change. To the unaided eye, it remains a small red spark. Its changing brightness made it mysterious to ancient observers, while modern exploration has turned that spark into a world with detailed geography. Jupiter shines brightly because it is the largest planet in the solar system. Even though it is far from Earth, its great size and reflective cloud tops make it easy to notice when it is well placed. Through binoculars, observers can often see 4 small points near Jupiter. These are the Galilean moons, Io, Europa, Ganymede, and Callisto. Their positions change from night to night as they orbit the planet, making Jupiter feel like a small system of its own. A telescope can reveal cloud bands across Jupiter's disk and, under good conditions, the Great Red Spot. To the eye alone, Jupiter looks calm and steady, but it is a giant world with fast rotation, powerful weather, and many moons. Its calm point of light carries a complex planetary scene. Saturn's rings are visible through small telescopes as a thin, bright system around the planet. Without a telescope, Saturn looks like a steady yellowish point, less brilliant than Venus or Jupiter, but still easy to find when conditions are good. The rings are not a solid band. They are made of countless icy particles, from tiny grains to pieces the size of boulders, all orbiting Saturn together. Their angle changes as Saturn and Earth move, so the rings can look wide open in some years and nearly edge-on in others. This slow change gives telescope observers a different view over time. The rings are broad but remarkably thin compared with their width. From Earth, they turn a single point of light into one of the most memorable sights in the night sky, a distant world surrounded by a delicate, orderly disk. Mercury is hard to see because it stays close to the Sun in Earth's sky. Its orbit lies inside Earth's orbit, so it never wanders far into the deep darkness of midnight. It usually appears low near the horizon shortly after sunset or shortly before sunrise. Because it is close to the horizon, its light must pass through more atmosphere, and buildings, hills, trees, or haze can hide it easily. Mercury can look like a small bright star, but it is often visible only during brief observing windows. Its closeness to the Sun made it difficult for ancient skywatchers to follow, even though it can be seen without a telescope. The planet's quick motion matches its short year around the Sun. In the night sky, Mercury feels like a small, shy visitor at the edge of twilight. Across the year, the Sun appears to follow a path called the ecliptic. At night, this same path helps explain where the Moon and planets are usually found. The solar system formed from a flattened disk of material, so most major planets orbit in nearly the same plane. From Earth, that plane appears as a broad line across the sky. The Moon stays close to it because its orbit is only slightly tilted compared with Earth's orbit around the Sun. When several planets are visible in one evening, they often seem to form a gentle arc along this path. The ecliptic is not painted on the sky, but it gives structure to many familiar movements. It is a subtle guide, showing that the wandering lights of night belong to one shared solar system. Along the Sun's apparent yearly path lie the zodiac constellations. Because the Moon and planets stay near the ecliptic, they pass through or near these same constellations as seen from Earth. The traditional zodiac signs grew from old sky divisions, but modern constellation boundaries are not all equal in size. Some zodiac constellations cover wider stretches of sky than others, so the Sun spends different amounts of time in each one. For stargazing, the zodiac is useful because it marks the zone where bright planets are most likely to appear. The stars themselves are far beyond the planets and do not control their motion. They form a distant background against which nearby solar system bodies move. The zodiac is a calm example of how ancient pattern making and modern astronomy can share the same sky. Orion is one of the most recognizable constellations because its bright stars form a clear winter pattern. In much of the northern hemisphere, it rises in the evening during the colder months and stands out with 3 stars in a straight belt. Around the belt are bright stars that mark the hunter's shoulders and feet, including reddish Betelgeuse and blue-white Rigel. Orion is not only a simple outline. It contains star-forming regions, bright nebulae, and young hot stars visible through telescopes. The constellation's shape has been noticed by many cultures, though interpreted in different ways. Its clear geometry makes it useful for finding nearby patterns, such as Taurus and Canis Major. When Orion climbs above the horizon, the night sky gains a strong, familiar figure made from distant, unrelated stars. For many southern observers, the Southern Cross is a small constellation that helps with direction. Officially called Crux, it is much smaller than many famous constellations, yet its bright cross shape is easy to remember under southern skies. It appears on several national flags and has long been important to navigation in the southern hemisphere. Because there is no bright southern pole star like Polaris, observers can use the long axis of the cross to estimate the direction of the south celestial pole. Nearby dark patches and rich Milky Way star fields make the region especially striking in clear dark skies. Crux shows how a compact pattern can hold practical value and cultural meaning. Its simple shape reminds us that the night sky changes with latitude, offering different guiding signs to different parts of the world. Circumpolar stars never set from certain latitudes because they circle close to a celestial pole. In the northern hemisphere, stars near Polaris can remain above the horizon all night and throughout the year. They do not rise and set in the familiar way, but trace continuous circles as Earth rotates. The farther north an observer travels, the larger the circumpolar region becomes. Near the North Pole, nearly all noticeable stars move in circles around the sky, while near the equator, very few are circumpolar. This pattern is mirrored in the southern hemisphere around the south celestial pole. Circumpolar stars gave people reliable reference points because they were always available when skies were clear. Their slow turning makes the night feel like a vast clock, with the pole as the still center of motion. To map the sky, astronomers often use the idea of a celestial sphere, as if the heavens formed a great dome around Earth. Stars are not actually fixed to a sphere, but the idea helps observers describe positions clearly. Astronomers use sky coordinates that work somewhat like longitude and latitude on Earth, allowing them to locate stars, galaxies, and nebulae. This system is practical because every object appears in a direction, even when its true distance is very different. The celestial poles mark where Earth's axis points, and the celestial equator is the projection of Earth's equator into space. These imagined lines and points do not exist physically, but they make the moving sky easier to map. The night sky can look like a simple dome overhead, and this simple model remains useful for finding real objects. Meteors are flashes of light caused by tiny pieces of space debris entering Earth's atmosphere. Most meteors begin with particles much smaller than a pebble. As they rush into the air at high speed, they heat the surrounding gases and create a bright streak. The glowing trail usually lasts only a moment, which is why meteors are often called shooting stars, though they are not stars at all. Many burn up high above the ground and never reach the surface. On a clear, dark night, patient observers may see occasional random meteors, even outside a major shower. Their sudden appearance brings motion to a sky that otherwise seems steady. A meteor is a small event, but it reveals Earth moving through a solar system that still contains scattered dust and fragments. Meteor showers happen when Earth passes through streams of debris left by comets, or, in some cases, asteroids. These streams spread along the parent object's orbit, so Earth meets them at about the same time each year. During a shower, meteors appear to come from one area of the sky called the radiant, though the particles are entering the atmosphere in parallel paths. The Perseids in August and the Geminids in December are among the better-known annual showers. The best viewing often comes after midnight, when the observer's side of Earth faces more directly into the stream. Moonlight, clouds, and city lights can reduce the number seen. A meteor shower is not a fall of stars, but a gentle crossing of paths between Earth and old trails of cosmic dust. Comets may appear after dark when icy bodies from the outer solar system come close enough to the Sun. A comet's solid nucleus is usually small compared with a planet, but sunlight can warm its surface and release gas and dust. This material forms a glowing coma around the nucleus, and sometimes one or more tails. The tail does not trail behind simply because of motion. It is shaped by sunlight and the solar wind, so it generally points away from the Sun. Many comets remain faint and need telescopes, while a few become bright enough to see without optical aid. Their visits can be predictable if their orbits are known, or surprising when newly discovered. A comet is a cold traveler from colder regions, briefly made visible by warmth and light. Zodiacal light is a faint glow caused by sunlight, reflecting from dust in the inner solar system. Under very dark skies, it can appear as a soft triangular beam rising from the horizon after evening twilight or before morning twilight. It follows the ecliptic, the same broad path used by the Sun, Moon, and planets. The dust comes from sources such as comets and asteroid collisions, spread thinly through the plane of the solar system. City lights and moonlight can easily hide zodiacal light, so many people never notice it. It is not an atmospheric glow like twilight, though it is seen through the atmosphere from the ground. This delicate light shows that space near the Sun is not perfectly clean. Fine dust catches sunlight and lays a pale veil along the night. Airglow is a natural faint light produced high in Earth's atmosphere. Even on a moonless night far from cities, the sky is not completely dark, partly because atoms and molecules in the upper atmosphere release small amounts of light. This glow is usually too subtle for the eye to notice clearly, but cameras can record it as soft bands or gentle color. Airglow is different from aurora, though both occur high above the ground. Aurora is driven by charged particles guided by Earth's magnetic field, while airglow is a more constant background effect connected with chemistry and sunlight's earlier influence on the upper air. For astronomers, airglow is one reason the night sky has a natural brightness limit. The darkness above us is alive with faint processes, even when it looks still. Auroras appear when charged particles from the Sun interact with Earth's magnetic field and upper atmosphere. They are most common near the polar regions, where magnetic field lines guide particles downward. When these particles excite gases high above the surface, the gases release light, often in green, red, purple, or blue tones. Auroras can form curtains, arcs, rays, or softly moving sheets across the sky. Their displays vary with solar activity, and strong geomagnetic storms can sometimes bring auroras farther from the poles. Though they can look delicate, they take place high above weather clouds, in a region where the atmosphere is extremely thin. For people beneath them, auroras can turn the night sky into a slow, luminous motion. They reveal a subtle connection between the Sun, Earth's magnetism, and the upper air. Artificial light can hide faint stars by brightening the sky above towns and cities. Streetlights, buildings, vehicles, and outdoor signs can scatter light through the atmosphere, creating a glow over towns and cities. This glow reduces contrast, making the Milky Way difficult or impossible to see from many populated places. It does not remove the stars, but it overwhelms their faint light before it reaches the eye clearly. Shielded lighting, warmer color choices, and using only the light that is needed can help protect dark skies. The issue matters for astronomy, but it also affects wildlife, energy use, and the human experience of night. When people travel from a bright city to a dark rural sky, they often discover that the overhead view has far more hidden depth than they expected. Human eyes adapt to darkness slowly, allowing fainter stars to appear over time. In bright light, the eye relies more on cone cells, which help with color and sharp detail. In dim light, rod cells become more important because they are sensitive to faint light, though they do not show color in the same rich way. Full dark adaptation can take many minutes, and a sudden bright light can reduce it quickly. This is why stargazers often use dim red lights, which tend to disturb night vision less than white lights. Looking slightly to the side of a faint object can make it easier to see, because rods are more concentrated away from the very center of vision. The night sky slowly opens as the eye changes, revealing quiet details that were present from the beginning. Binoculars reveal details that the eye alone often misses. They gather more light than the pupils alone and make faint objects easier to notice, while still showing a wide, natural-looking field. With binoculars, the moon's craters become clearer. Star clusters gain many more points, and Jupiter's largest moons may appear as tiny companions. They are often easier to use than a telescope because both eyes remain involved and the view is not extremely magnified. A steady hold or simple support can make the image much calmer. Binoculars are especially good for sweeping along the Milky Way, where star fields and dark lanes create rich patterns. They do not replace large telescopes, but they offer a gentle doorway into the hidden layers of the wide night sky, far above us. High in Taurus, the Pleiades forms a young star cluster that looks like a tiny dipper of blue-white stars. It is found in the constellation Taurus and is one of the most famous clusters visible to the eye alone. Many people see 6 or 7 bright stars, while binoculars reveal far more. The stars are physically related, born from the same general cloud of gas and dust, and they travel through space together. Long exposure photographs show faint reflection nebulae around them, where dust reflects starlight in a soft glow. The Pleiades has been important in many cultures because it is easy to recognize and tied to seasonal changes. Unlike a constellation, this cluster is a real stellar family. Its compact sparkle gives the night sky a sense of closeness overhead, even across hundreds of light years. Below Orion's belt, the Orion Nebula appears as a nearby star-forming region and a faint misty patch. With the eye alone under decent conditions, it may look like a small misty spot in Orion's sword. Binoculars and telescopes reveal more of its cloudy structure, while photographs show glowing gas shaped by young, hot stars. The nebula is a nursery where new stars are forming from cold gas and dust. Its light comes partly from gas energized by nearby stars, especially young, massive ones in the central region. The Orion Nebula is important because it allows astronomers to study star birth relatively close to Earth in galactic terms. In the winter sky, it appears soft and still, but it is an active place where gravity, radiation, and matter are shaping future suns slowly. Under dark skies, many people can glimpse the Andromeda Galaxy, one of the farthest objects noticeable to the eye alone. It appears as a faint oval smudge in the constellation Andromeda, often easier to find with binoculars. This soft patch is not a cloud inside the Milky Way, but a separate spiral galaxy containing hundreds of billions of stars. Its light has traveled for about 2.5 million years before reaching Earth. Even though Andromeda is large, distance spreads its glow across the sky, so it looks dim to our eyes. It is moving toward the Milky Way, and the two galaxies are expected to merge far in the future. For a patient observer, Andromeda is a gentle doorway beyond our own galaxy, a reminder that the night sky extends far past the stars we can individually see. On the Moon, the terminator is the moving line between lunar day and lunar night. Along this boundary, sunlight strikes the surface at a low angle, casting long shadows from crater rims, mountains, and ridges. These shadows make details easier to see through binoculars or a telescope than they are during a full moon, when sunlight falls more directly and the surface can look flatter. The terminator slowly shifts as the moon moves through its phases, revealing new areas night by night. A crater that was hidden in darkness one evening may stand bright and sharp the next. This is why many lunar observers prefer the moon when it is partly lit rather than completely full. The changing line of light turns the moon into a shadowed landscape, where depth appears softly through shadow. Earthshine is the faint glow that can reveal the dark part of a crescent moon. When the moon is a thin crescent, sunlight reflects from Earth onto the moon's night side, then reflects back toward us. This double reflection is gentle, so the unlit part of the moon appears dim and grey beside the bright crescent. The effect is sometimes described as the old moon in the new moon's arms. It is easiest to notice when the crescent is slim and the sky is dark enough, but not yet too crowded with glare. Earthshine shows that Earth itself is bright from the moon's point of view, with clouds, oceans, ice, and land sending sunlight back into space. A small crescent can quietly reveal that our planet also lights the sky of another world. A lunar eclipse happens when Earth passes between the Sun and the Moon. During this alignment, the Moon moves through Earth's shadow, and the bright full moon can darken or turn a coppery red. The red color appears because some sunlight bends through Earth's atmosphere before reaching the moon, while shorter blue light is scattered more strongly. The exact shade can vary depending on dust, clouds, and conditions in Earth's air at the time. Lunar eclipses are safe to watch without special equipment, unlike solar eclipses, and they can last long enough to feel slow and steady. They only happen at full moon, but not every full moon becomes an eclipse because the moon's orbit is tilted. A lunar eclipse links the Sun, Earth, Moon, and atmosphere in one calm shadow. A solar eclipse occurs when the moon passes between Earth and the Sun. From the ground, this can happen only when the alignment is precise enough for the moon to cover part or all of the Sun's disk. Total solar eclipses are possible because the Sun and Moon appear nearly the same size in our sky, even though the Sun is much larger and much farther away. The Moon's shadow falls on a narrow path across Earth, so totality is visible only from certain places. Solar eclipses require proper eye protection, except during the brief period of totality, when the moon completely covers the Sun's bright face. Though they are daytime events, they belong to the same sky system seen at night. The moon that glows softly after sunset can, at rare moments, briefly hide the sun itself. Occultations happen when the moon or another nearby body passes in front of a more distant object. The moon can cover stars, planets, or even parts of star clusters as it moves along its orbit. To an observer on Earth, a star may suddenly vanish behind the moon's dark edge and later reappear from the opposite side. These events reveal the moon's steady motion across the background sky. Because the moon is close, the exact timing and visibility of an occultation depend on where the observer stands on Earth. Astronomers can use such events to refine positions, study lunar features, or measure details of distant objects. For a casual stargazer, an occultation feels simple and calm. One bright point disappears, not because it has changed, but because the moon has crossed the line of sight. Conjunctions occur when two bright objects appear close together in the sky. The objects may be widely separated in space, but from Earth, they line up in nearly the same direction. The moon often forms striking conjunctions with Venus, Jupiter, Saturn, or Mars, creating a temporary pairing that can be easy to notice after sunset or before sunrise. Planets can also appear close to one another, sometimes making a compact grouping along the ecliptic. A conjunction does not mean the objects are physically near each other. It is a matter of perspective, like distant lanterns seen along the same road. These meetings can last for one evening or change gradually over several nights. They give the night sky a gentle sense of arrangement as familiar lights gather and separate in their own gentle rhythms. As the seasons pass, different constellations appear in the evening sky. As Earth travels around the sun, the nighttime side of the planet faces different directions in space during different parts of the year. This is why Orion is a winter evening pattern for many northern observers, while Scorpius is more associated with summer evenings. Some circumpolar constellations remain visible year-round from certain latitudes, but many others rise and set with the seasons. The stars themselves have not moved enough to create this yearly change. The shift comes from Earth's orbit, carrying us to a new viewing angle around the sun. Seasonal skies helped people mark planting, harvesting, travel, and ceremony long before modern calendars. The night sky is a slow yearly circle, as well as a nightly turning. From every observing place, the horizon hides part of the sky. At any one moment, only about half of the celestial sphere is above the horizon. The rest lies below the ground, blocked by the curve of the planet itself. As Earth rotates, new stars rise while others set, allowing more of the sky to become visible across the night. Latitude decides which parts of the sky can ever be seen from a location. Far northern observers never see some southern constellations, while far southern observers never see some northern ones. Mountains, trees, buildings, haze, and light pollution can reduce the practical horizon even more. The visible sky is always a local window into space, shaped by Earth's roundness and by the landscape around the observer. Astronomers use magnitude as a brightness scale for objects in the sky. The system began in ancient astronomy, where the brightest stars were called first magnitude, and fainter visible stars were placed in higher numbered groups. Modern astronomy kept the pattern, but made it precise. Lower numbers mean brighter objects, and very bright objects can have negative magnitudes. Venus, the full moon, and the Sun are examples of objects with negative values. The scale can feel backward at first, but it reflects a long history of skywatching. Magnitude helps observers compare stars, planets, comets, and deep sky objects in a shared way. It also reminds us that human eyes notice brightness in steps rather than simple straight amounts. A calm point of light overhead can be measured, compared, and placed into a wider order. A star cluster is a group of stars born near one another from the same cloud. Open clusters, such as the Pleiades, are usually found in the disk of the Milky Way and often contain young stars loosely held together by gravity. Over time, passing stars and galactic tides can spread an open cluster apart. Globular clusters are different. They are dense, rounded swarms of very old stars, often found around the halo of the galaxy. Through binoculars or small telescopes, some clusters appear as misty patches, while larger instruments can break them into many points. These clusters show that stars are not always scattered alone. Many begin life in groups, and some remain gathered for immense spans of time, adding soft knots of light to the night sky. Nebulae are clouds of gas and dust that can appear as faint patches among the stars. Some glow because nearby, hot stars energize their gas, causing it to release light. Others shine by reflecting starlight, while some appear dark because thick dust blocks the stars behind them. To the unaided eye, only a few nebulae are visible under good conditions, and they often look pale and subtle. Cameras reveal their colors and shapes far better than human night vision can. Nebulae are important because they are connected with star birth, star death, and the recycling of material inside galaxies. They are not empty mist, but matter spread across vast regions. In the dark sky, a nebula may look like a small blur, yet it can be a place where cosmic material is changing form. Dark nebulae are noticeable because they block light from stars behind them. They are made of cold gas and dust, often thick enough to create shadowy shapes against the brighter Milky Way. In a dark sky, some dust lanes can be seen as uneven gaps in the pale galactic band. These are not holes where stars are missing, but clouds in the foreground hiding more distant light. Dark nebulae can contain dense regions where gravity may eventually gather material into new stars. Their darkness is therefore not empty or inactive. It can be the sign of cold matter waiting in deep space. The contrast is easiest to notice where the Milky Way is bright behind it. A dark patch in the night sky may be a cloud with its own hidden structure. Double stars show that some points of light are really two stars close together in the sky. Some are true binary systems, where two stars orbit a shared center of mass. Others are optical doubles, where unrelated stars happen to line up from Earth's viewpoint. Telescopes can split many double stars into separate points, sometimes with contrasting colors that make them especially pleasing to observe. Binary stars are important because their motion helps astronomers measure stellar masses. This is one of the main ways scientists learn how heavy different kinds of stars can be. To the eye alone, many of these systems blend into a single point, hiding their partnership. A calm star may not be alone at all. It may be part of a long gravitational dance, too distant to separate without help. Variable stars change brightness over time for several different reasons. Some expand and contract in steady pulses, becoming brighter and fainter as their size and temperature shift. Some vary because one star in a binary system passes in front of another, blocking part of its light from our view. Others change because of eruptions, spots, or other activity on or near the star. A few variable stars can be followed without optical aid, while many more require binoculars, telescopes, or sensitive cameras. Their changes may take hours, days, months, or longer. Variable stars helped astronomers measure distances in space, especially certain pulsating stars with predictable patterns. To a casual observer, the stars can seem fixed and unchanging. Careful watching reveals that some of them breathe in brightness across time. Moonlight can make faint stars harder to see by brightening the dark background. Around full moon, its reflected sunlight spreads through the atmosphere and reduces contrast, much like a smaller version of twilight. Bright stars and planets remain visible, but the Milky Way, faint meteors, dim galaxies, and delicate nebulae can fade from view. This is why many stargazers plan deep sky observing around the new moon, when the lunar disk is hidden in the sun's direction. The moon itself becomes a beautiful target when it is bright, so moonlit nights are not wasted. They simply favor different kinds of observing. A full moon can wash the sky in silver and soften the faintest details, while a moonless night can reveal the deeper background beyond it. Near the horizon, the moon can seem much larger than it does high overhead. The moon's actual angular size changes only slightly during the night, so the dramatic difference people notice is mostly a perception effect. When the moon is low, the brain sees it near trees, buildings, hills, or distant landscape features, and this context can make it seem unusually large. When the same moon is high in an open sky, there are fewer familiar objects nearby for comparison. Photographs taken with the same lens can show that the moon size on the image remains nearly the same. The illusion is old, common, and still studied as part of human perception. It adds a quiet wonder to moonrise, when a familiar object seems to become enormous without truly changing. Stars near the horizon often look dimmer and more colorful because their light crosses more atmosphere. At a low angle, starlight travels through a thicker path of air than it does when the star is high overhead. The atmosphere scatters and absorbs some of the light, weakening it before it reaches the eye. Moving air layers also disturb the light more strongly, causing extra twinkling and flashes of color. This is why bright stars near the horizon can shimmer red, blue, green, or white in quick changes. The effect comes from Earth's air rather than from rapid changes in the star itself. Higher in the sky, stars usually appear steadier and clearer. The horizon gives the night sky a soft, unstable edge, where distant light is filtered by the planet's atmosphere. Artificial satellites appear as steady moving points crossing the dark sky. They shine because they reflect sunlight while passing high above Earth, often after sunset or before sunrise when the ground is dark, but the satellite is still sunlit. Unlike aircraft, many satellites do not blink with navigation lights, and they usually move smoothly across the stars. Some fade as they enter Earth's shadow and stop reflecting sunlight toward the observer. The International Space Station can become especially bright during favorable passes, sometimes outshining nearly everything except the moon and bright planets. A pass may last only a few minutes, with the station gliding like a clear white point from one side of the sky to another. Satellites are human-made objects, but they have become part of modern stargazing. Their motion reminds us that the view above Earth now contains both ancient lights and small traces of technology circling the planet. Telescope views depend on both the instrument and the air above it. A larger telescope can gather more light and show fainter objects, but atmospheric steadiness often limits how sharp the image appears. Astronomers call this steadiness seeing. On nights of poor seeing, planets may ripple and stars may blur, even through excellent equipment. Transparency is different. It describes how clear the air is, especially for seeing faint objects. A night can be steady but hazy, or transparent but turbulent. Temperature changes, wind, moisture, dust, and local heat rising from roofs or pavement can all affect the view. This is why observatories are often built on high, dry, stable sites, away from bright cities. Looking into space from the ground always means looking through a moving ocean of air. Space telescopes avoid the blurring and blocking effects of Earth's atmosphere. From orbit or deep space positions, they can observe the universe without looking through turbulent air, city glow, clouds, or most atmospheric absorption. This allows sharper images and access to kinds of light that do not reach the ground well, such as much ultraviolet and infrared radiation. Space telescopes have revealed faint galaxies, star-forming clouds, planetary atmospheres, and details of objects that ground-based observers once could not see clearly. They do not replace human stargazing, because the unaided night sky still offers a direct connection to the wider universe. Instead, they extend that view. The same stars that look like small points from a quiet field can become rich structures when seen from above the atmosphere. A light year is a distance. Even though its name contains the word year, it describes how far light travels through space in 1 year, at a speed so fast that ordinary distances become too small to use comfortably. The nearest stars beyond the Sun are several light years away, meaning their light takes several years to reach Earth. More distant stars may send light that has traveled for hundreds or thousands of years before appearing as a point in the night sky. Galaxies carry this idea much farther, with light crossing millions or billions of years before reaching our telescopes. Looking up does not change the present moment on Earth, but it does fill the view with old light arriving now. The night sky is therefore a quiet mixture of distance and time, held together by the steady travel of light. Because light takes time to travel, every view of the sky carries a built-in delay. The moon is close enough that its light reaches Earth in a little over 1 second, while sunlight reflected from planets may take minutes or more to arrive. Starlight takes years because stars are much farther away. When astronomers observe a distant galaxy, they are seeing light that left when that galaxy was younger. This does not mean time is strange in a magical way. It is simply the result of light needing time to cross space. Every view of the universe is a view shaped by travel time. Even the familiar moon is seen not exactly as it is at this instant, but as it was a moment ago. The night sky gently reminds us that seeing and arriving are not always the same thing. Proper motion is the slow drift of stars across the sky over long periods of time. Stars are not fixed in place, even though they seem still during a human lifetime. Each star moves through the galaxy, and the Sun moves as well. Because the distances are so large, most stellar motion appears extremely small from Earth, often needing careful measurements over years or decades to detect. A few nearby stars show faster apparent movement because they are close enough for their motion to stand out. Over tens of thousands of years, familiar constellation shapes will gradually change. Orion, the Big Dipper, and other patterns are temporary from a cosmic point of view. The night sky feels permanent because human lives are brief beside stellar motion, but the star patterns are slowly flowing. Precession slowly changes the direction of Earth's axis over thousands of years. Earth spins like a slightly tilted top, and its axis traces a slow circle in space rather than pointing forever toward the same star. Because of this motion, the North celestial pole shifts gradually among the background stars. Polaris is the current North Star, but it was not always the best pole star, and it will not remain so forever. Precession also changes how the coordinates of stars are recorded over long periods. Ancient sky maps and modern sky maps must account for this slow wobble. The change is not noticeable from night to night, or even from year to year without precise tools. It is a quiet movement of Earth itself, gently altering the sky's reference points across deep time. Different latitudes on Earth reveal different parts of the sky. Someone in Northern Europe sees Polaris above the northern horizon and many familiar northern constellations, while someone in Australia sees southern stars that never rise high, or never rise at all, in the north. The reason is simple. Each location faces space from a different angle on Earth's curved surface. Near the equator, observers can see a wider mix of northern and southern skies over the course of a year. Near the poles, the sky circles around one high celestial pole, and the opposite half of the sky stays hidden. This makes stargazing a local experience. The universe is the same, but Earth's roundness decides which part of it becomes the observer's nightly ceiling. Towards Sagittarius lies the center of the Milky Way. From Earth, this region appears in the richest part of the Milky Way band, especially visible from dark southern or low northern skies during the right season. The actual center is hidden from ordinary visible light by thick clouds of dust between us and the galactic core. Infrared and radio observations can pass through much of that dust, revealing dense star fields and the powerful object at the galaxy's heart. To the eye alone, the region may look like a bright, uneven glow crossed by dark lanes. It is not the center of the universe, but it is the center of our home galaxy. A soft summer Milky Way can therefore point toward the deep, crowded middle of the stellar system that contains us. Dark lanes run through the Milky Way, where interstellar dust blocks and reddens starlight. These dust grains are tiny, but spread across enormous distances, they can hide whole regions of background stars. In photographs, the dust may look like torn shadows running through bright star fields. To the eye under dark skies, it can make the Milky Way appear patchy rather than smooth. This dust is not dirt in the ordinary earthly sense. It includes small particles made from elements formed in stars and spread into space over time. Dust can cool, gather with gas, and become part of future star-forming clouds. The dark lanes are therefore not simply places where light is missing. They are part of the galaxy's material cycle, quietly shaping what can be seen and what may later be born. Within the Milky Way, stars orbit the galaxy's center. The Sun is one of those stars, traveling around the galactic center along with its planets, moons, asteroids, and comets. This orbit is extremely slow by human standards, taking hundreds of millions of years to complete. During one human lifetime, the motion is impossible to sense directly by looking at the sky. Yet the whole solar system is moving through the galaxy at great speed. The constellations look stable because the distances are immense and the timescales are long. Galactic motion is a reminder that stillness in the night sky is often a matter of perspective. The stars are not pinned to a dark background. They are members of a vast rotating system, moving together through space with calm patience. Redshift helps astronomers understand that many distant galaxies are moving away from us. When light from a galaxy is stretched toward longer, redder wavelengths, It carries evidence about the expansion of space between galaxies. This does not mean every object in the night sky is simply flying away through ordinary space like sparks from a fire. Nearby galaxies can move in different ways because gravity still matters strongly on local scales. But on the larger scales, more distant galaxies tend to show greater redshift. This pattern helped reveal that the universe itself has changed over time. Redshift is not visible to the unaided eye when looking at a faint galaxy, but it can be measured with instruments that split light into its colors. A small smudge in the sky can carry a record of cosmic expansion. Spectroscopy lets astronomers read starlight by spreading it into a spectrum. When light is separated into its colors, dark or bright lines can appear at specific places. These lines reveal which elements are present in a star, nebula, or planet's atmosphere, because atoms and molecules interact with light in recognizable ways. Spectroscopy can show temperature, motion, rotation, composition, and magnetic activity. It turned astronomy from a science of positions and brightness into a science of physical understanding. A star may look like a simple white point to the eye, but its light contains a detailed signature. With the right instrument, that point can tell a story about hydrogen, helium, metals, pressure, and movement. The night sky is not silent to science. It speaks through the fine structure of light. Exoplanets can be found by watching stars dim very slightly. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light. This is called the transit method. The dimming is usually far too small to notice by eye alone, but sensitive instruments can measure it. Repeated dips in brightness can reveal the planet's orbital period and size compared with the star. Other methods can detect the star's small wobble under the planet's gravitational pull. Most exoplanets are not directly visible as little dots beside their stars, because the stars are much brighter and the planets are faint. Still, many worlds have been found this way. A calm star in the night sky may have planets circling it, hidden inside its steady light. Some satellites draw attention because of the way they reflect sunlight. Classic iridium flares were once bright, predictable flashes from a specific group of communication satellites, whose polished antenna surfaces briefly sent sunlight toward Earth. Many of the original satellites that produced those famous flares have since been replaced or removed, so such events are much less common than they once were. Starlink satellites can create a different sight, especially shortly after launch, when several may cross the sky in a line before spreading into their working orbits and becoming fainter. Their visibility depends on sunlight, altitude, observer location, and the darkness of the ground below. These moving lights are not stars, meteors, or aircraft formations, but reflections from objects in orbit. They show how the modern sky can hold small mirrors above us, bright for a moment because angle and sunlight briefly agree. For optical observatories, the best sites are often high, dry, dark and stable. High mountains place telescopes above much of the thicker lower atmosphere, reducing haze and water vapor. Dry air helps because moisture can scatter light and block some wavelengths. Dark surroundings matter because artificial light can wash out faint astronomical targets. Stable air reduces blurring, allowing sharper views of stars and planets. This is why many major observatories are built in places such as remote deserts, volcanic mountains, or high plateaus. The location is part of the instrument. A telescope does not work alone. It works with the sky above it and the ground around it. Good observing sites are quiet partnerships between geography, weather, darkness, and the careful design of human tools. Radio astronomy reveals parts of the universe that human eyes cannot see. Many objects in space give off radio waves, including gas clouds, galaxies, pulsars, and regions near black holes. Radio telescopes use large dishes or networks of antennas to collect these long wavelengths. Because radio waves can pass through some dust that blocks visible light, they help astronomers study hidden regions such as the center of the Milky Way. Radio observations do not depend on darkness in the same way optical stargazing does, and some can be made during the day. Still, they are studying the same universe that shines above us at night. The visible sky is only one layer. Beyond it are quieter signals, arriving steadily from cold gas, distant galaxies, and energetic objects far across space. Pulsars are rapidly spinning neutron stars that send beams of radiation into space. A neutron star is the dense remnant left after some massive stars explode at the end of their lives. If its beam sweeps across Earth, instruments detect a pulse each time the star rotates, like a lighthouse beam passing an observer. Some pulsars spin many times per second, while others rotate more slowly. Their timing can be astonishingly regular, making them useful for studying gravity, dense matter, and motion in space. Pulsars are usually not visible to the eye alone, but they belong to the wider night sky revealed by radio and high-energy astronomy. They show that the universe contains clocks made from collapsed stars. In the darkness between familiar constellations, some objects are turning with remarkable steadiness. Black holes do not shine by themselves, but their surroundings can reveal them. A black hole is a region where gravity is so strong that light cannot escape from inside its boundary. If gas, dust, or stars move near it, that material can heat up and glow before crossing the point of no return. Some black holes are found by watching nearby stars orbit an unseen mass. Others are detected through X-rays, radio waves, or the motions of gas around galactic centers. The Milky Way's central black hole is not visible as an ordinary point in the night sky, but its presence has been measured through the movements of stars near the galactic core. Black holes add invisible structure to the sky, reminding us that not everything important in the universe announces itself with visible light. Supernovae can briefly make a star shine as brightly as an entire galaxy. They happen when certain stars end their lives in powerful explosions, or when some white dwarfs in binary systems are driven beyond stability. From Earth, a supernova in a distant galaxy may appear as a new point of light where none was seen before. Historical supernovae inside the Milky Way were sometimes bright enough to be noticed by skywatchers without telescopes. These events spread heavy elements into space, helping enrich future generations of stars and planets. They are rare in any one galaxy, so astronomers watch many galaxies to find them. Though the event itself is violent, its long-term role is transformative. The atoms in rocky worlds and living bodies are connected, in part, to stars that once ended by seeding space. In Taurus, the Crab Nebula is the expanding remnant of a supernova seen from Earth in the year 1054. Today, it appears through telescopes as a faint, complex cloud in the constellation Taurus. At its center is a pulsar, a rapidly spinning neutron star left behind by the explosion. The nebula continues to expand, carrying material outward into space. Its light is produced by energetic particles and magnetic fields, making it important for many kinds of astronomy. To the eye alone, the Crab Nebula is not a bright showpiece, but instruments reveal it as one of the most studied objects in the sky. it connects human historical records with modern astrophysics. A recorded new star from nearly 1,000 years ago has become a quiet laboratory for learning how stellar remnants evolve. Hidden from Earth, the Moon's far side is not the same as a permanently dark side. Because the Moon keeps nearly the same face turned toward Earth, people sometimes call the hidden half the dark side, but this is misleading. The far side receives sunlight during its own lunar day, just as the near side does. When the Moon is new from Earth, the far side is mostly sunlit. When the Moon is full from Earth, the far side is mostly in night. Spacecraft first revealed its surface directly, showing a heavily cratered landscape with fewer dark maria than the side we know. The far side is simply the side turned away from Earth. It is hidden by geometry, not by endless darkness, and it reminds us that even the familiar Moon has a quiet hemisphere beyond ordinary view. Libration lets observers glimpse a little more than half of the Moon over time. Although the Moon always keeps the same general face toward Earth, its orbit is not a perfect circle, and its speed changes slightly along the way. Its axis is also tilted a little compared with its orbit. These small effects make the Moon appear to rock gently from side to side and nod slightly up and down across the month. Because of this, careful observers can see around the edges, gaining views of regions near the lunar limb that are sometimes hidden and sometimes revealed. In total, more than half of the lunar surface can be seen from Earth across time, though never all at once. The Moon's face is steady, but not perfectly frozen. It offers small, slow changes at its margins. Stars rise about 4 minutes earlier each night because Earth moves around the Sun. Earth makes one rotation relative to the distant stars in about 23 hours and 56 minutes, a period called a sidereal day. The ordinary solar day is a little longer, because Earth must turn slightly more for the Sun to return to the same position in the sky. This small difference adds up night after night. A constellation seen at 10 o'clock one evening will appear in nearly the same place about 4 minutes earlier the following evening. Over a month, the shift becomes roughly 2 hours. This is one reason seasonal constellations slowly take over the evening sky. The stars keep their distant positions, but Earth's orbit changes when we face them after sunset throughout the year. Retrograde motion makes a planet seem to reverse direction against the background stars. Most of the time, planets drift eastward along the zodiac from night to night. During certain parts of their orbits, however, a planet can appear to slow, stop, and move westward for a while before resuming its usual path. This apparent reversal is caused by perspective, as Earth and the other planet move around the Sun at different speeds. For outer planets such as Mars, Jupiter, and Saturn, retrograde motion happens when Earth catches up and passes them on its inner, faster orbit. The planet is not truly turning backward in space. It only looks that way from our moving viewpoint. Retrograde motion was once a major puzzle, and it became a key clue that planets orbit the Sun. Opposition is often the best time to observe an outer planet. An outer planet reaches opposition when Earth lies between that planet and the Sun, placing the planet opposite the Sun in our sky. Around this time, the planet rises near sunset, stays visible through much of the night, and sets near sunrise. It is also usually closer to Earth than at many other points in its orbit, so it appears brighter and larger through telescopes. Mars can change especially strongly from one opposition to another because its distance from Earth varies a great deal. Jupiter and Saturn show steadier but still noticeable observing seasons. Opposition does not make a planet physically different. It simply gives Earth a favorable view, with sunlight falling on the planet and its bright side turned toward us. Uranus is faint enough that it was not recognized as a planet in ancient sky traditions. Under very dark skies and good conditions, it can sometimes be seen without optical aid as a dim point, but it moves slowly and does not stand out like Mercury, Venus, Mars, Jupiter, or Saturn. In 1781, William Herschel observed it with a telescope and first thought it might be a comet. Further observations showed that it followed a planetary orbit beyond Saturn. Uranus has a pale blue-green color in telescopes because methane in its atmosphere absorbs redder light and leaves more blue light reflected back. To the eye, it is modest and easy to overlook. Its discovery widened the known solar system and showed that the night sky still held major objects beyond the familiar ancient planets. Neptune was found after astronomers noticed that Uranus was not moving exactly as expected. The small differences in Uranus's path suggested that a more distant planet might be tugging on it through gravity. Calculations pointed to where such a planet could be, and telescopic observations in 1846 confirmed Neptune near the predicted region of sky. Neptune is too faint to see without optical aid, so it belongs to the telescopic night sky rather than the traditional naked eye one. It appears as a small bluish disk through powerful instruments, though much detail is difficult from Earth. Its discovery showed the strength of mathematics joined with observation. A planet too dim for human eyes alone was brought into knowledge by measuring the subtle pull it placed on another distant world, far away. Asteroids usually appear as faint points of light that move slowly among the stars. Most known asteroids orbit the Sun in the broad region between Mars and Jupiter, though many others follow different paths. They are rocky or metallic remnants from the early solar system, not bright enough to show shape through ordinary backyard views. A few, such as Vesta, can become bright enough to see without optical aid under excellent conditions, but most require binoculars, telescopes, or photographs. Over several nights, an asteroid's motion can reveal itself as it shifts against the fixed star background. It may look like an ordinary star at first, but its changing position gives it away. These small bodies add a smaller scale to the night sky, between planets, dwarf planets, and nearby dust. Dwarf planets are usually too distant and faint for casual night sky viewing. Pluto, Eris, Haumea, Makemake, and other distant bodies do not shine brightly enough for the eye alone, and most require careful telescopic work to detect. Pluto was discovered in 1930 by comparing photographic plates and noticing a tiny point that shifted position. Its faintness reflects both its small size and its great distance from the Sun. Dwarf planets are not failed planets in a simple sense. They are worlds that orbit the Sun, but have not cleared their orbital neighborhoods in the way major planets have. Their discovery helped astronomers understand the outer solar system as a crowded region, not an empty frontier. The night sky contains far more solar system members than the bright wanderers visible to the eye. Beyond Neptune, the Kuiper Belt forms a distant region of icy bodies. Most of its objects are far too faint to see without large telescopes, but they help explain the larger architecture of the solar system. Pluto is one of its best-known members, along with many smaller icy worlds. These bodies are leftovers from the solar system's formation, preserved in a cold outer zone where sunlight is weak. Some short-period comets may have origins connected with this region or nearby scattered populations. The Kuiper belt does not appear as a band of light in the night sky. It is known through patient observation of tiny moving points and careful orbit studies. Its existence gives depth to the darkness beyond the planets, showing that the solar system fades outward through many small worlds. Far beyond the planets, the Oort cloud is a possible distant reservoir of icy bodies surrounding the solar system. It has not been directly seen as a glowing shell in the night sky, but it is inferred from the paths of long-period comets that arrive from many directions. These comets can take thousands or even millions of years to orbit the Sun. The Oort cloud, if understood correctly, lies far beyond the planets and the Kuiper belt, where the Sun's gravity is weak but still important. Passing stars and galactic tides may disturb some icy bodies, sending them inward as comets. The idea helps explain why some comets appear from the deep dark with very long orbits. A sudden comet in the sky may have begun its visible visit in a remote and calm outer storehouse. Star names preserve traces of many languages, cultures, and observing traditions. Some of the most familiar names used in modern astronomy, such as Aldebaran, Deneb, and Betelgeuse, have roots in Arabic star lore and medieval transmission of astronomical knowledge. Other names come from Greek, Latin, or later catalogue traditions. Different cultures have given the same stars different meanings, grouping them into animals, tools, ancestors, rivers, or seasonal signs. Modern astronomy uses standardized names and catalogue numbers for precision, but older names remain common because they are memorable and rich with history. A bright star can therefore carry more than light. It carries a record of people watching the sky across deserts, seas, farms, mountains, and cities, naming fixed points above them to make the wide night more familiar above them. Vega, Deneb, and Altair form the bright asterism known as the Summer Triangle. It is not an official constellation, but a large pattern connecting 3 stars in 3 separate constellations: Lyra, Cygnus, and Aquila. In northern summer evenings, it rises high and becomes a useful guide to the Milky Way, which passes through the region near Deneb and Altair. The 3 stars look like a simple triangle, but they are very different in distance and true brightness. Deneb is vastly more luminous than it appears compared with nearby Vega, because it is much farther away. Altair is closer and spins rapidly, giving it a slightly flattened shape measured by modern instruments. The pattern is easy to recognize, yet it quietly contains depth, stellar variety, and a path into the rich star fields of summer. Around Orion, the winter circle forms a large pattern of bright stars. Often called the winter hexagon, it includes stars such as Sirius, Procyon, Pollux, Capella, Aldebaran, and Rigel, depending on how the pattern is drawn. From northern latitudes, it dominates many clear winter evenings with a wide ring of strong points. Each star belongs to its own constellation and lies at its own distance, so the circle is not a physical structure in space. It is a grand line-of-sight pattern made by Earth's viewing angle. The region contains many notable objects, including star clusters, nebulae, and the bright path of the Milky Way. The winter circle shows how the eye can gather separate stars into one calm shape, turning a cold seasonal sky into a broad and memorable celestial frame. From the southern hemisphere, the Magellanic Clouds appear as neighboring galaxies. There, they look like 2 soft patches of light separated from the main band of the Milky Way. known as the Large and Small Magellanic Clouds. They are companion galaxies interacting gravitationally with our own. To the eye alone, under dark southern skies, they can look like detached pieces of the Milky Way, but telescopes reveal star clusters, nebulae, and rich structure inside them. The Large Magellanic Cloud contains the Tarantula Nebula, one of the most active star-forming regions in the nearby universe. These galaxies are not noticeable from much of the far northern hemisphere, which makes them part of the special character of southern skies. They show that the night can reveal not only stars within our galaxy, but nearby galaxies beside it. In the southern hemisphere, observers can see the nearest bright star system to the Sun. Alpha Centauri appears as a bright point in the constellation Centaurus, but telescopes show that it is a multiple star system. Two Sun-like stars, Alpha Centauri A and B, orbit one another, while Proxima Centauri, a much dimmer red dwarf, lies nearby in space and is currently the closest known star to the Sun. Proxima is too faint to see without a telescope. Alpha Centauri is important not only because of its closeness, but because it gives southern observers a direct visual link to our stellar neighborhood. In the sky, it looks like one bright star among many. In reality, it is a nearby system, reminding us that even the closest stars remain separated by enormous distances. In the bright southern Milky Way, some cultures form patterns from shadow instead of stars. In parts of the southern hemisphere, especially where the Milky Way is bright, dark dust clouds stand out strongly against the starry background. Some Aboriginal Australian sky traditions describe the emu in the sky, a figure traced through these dark regions rather than by connecting bright points. This shows that the night sky can be read in more than one way. Bright stars invite lines and shapes, but dark nebulae can also become meaningful forms. The same galactic dust that astronomers study as cold material has also shaped human stories and seasonal knowledge. A patch of darkness can be as important as a spark of light when the sky is clear enough to notice it. Astronomical twilight ends when the sun is far enough below the horizon for the sky to become fully dark for most observing. Twilight is divided into civil, nautical, and astronomical stages, based on how far the sun has sunk below the horizon. During civil twilight, there is still enough natural light for many outdoor activities. Nautical twilight is darker, and the horizon may still be useful for navigation at sea. Astronomical twilight is the dimmest stage, when the remaining glow of the sun no longer strongly interferes with most night sky observing. At high latitudes in summer, the sun may not sink low enough for full astronomical darkness, leaving the night softly bright. Darkness is therefore not a sudden switch. It arrives by degrees as Earth turns an observer deeper into shadow. Dark sky preserves protect places where the natural night can still be seen clearly. These areas use careful lighting rules, public education, and land management to reduce artificial sky glow. The goal is not to remove human life from the night, but to light the ground wisely while keeping the sky as dark as possible. Such places help astronomers support nocturnal wildlife, save energy, and give visitors a chance to see the Milky Way, faint constellations, meteor showers, and subtle air glow. A protected dark sky can feel ancient because it resembles the view most humans knew before widespread electric lighting. It is also modern because preserving it requires deliberate choices. The night sky is part of the natural environment, and darkness itself can be cared for like clean water or quiet land. Above us, The dark sky is a shared record of nature, motion, and human attention. Its lights include nearby reflections from the moon and planets, stars at many distances, faint galaxies, passing meteors, artificial satellites, and subtle glows from Earth's own atmosphere. Some patterns repeat nightly, some return season by season, and some change over centuries or longer. People have used the sky for calendars, travel, storytelling, science, and simple wonder. Modern instruments reveal far more than the unaided eye can see, yet the basic act of looking upward remains direct and familiar. The sky does not need to be dramatic to be rich. A calm, dark evening can hold geology on the moon, weather on planets, dust between stars, old light from galaxies, and the steady turning of Earth beneath every observer. And so, our calm journey through the sky comes to a close. We have looked at the moon as a changing world of shadows and sunlight, at planets wandering along the ecliptic, at stars whose colors and brightness carry clues about their nature, and at galaxies whose faint light reaches us from far beyond the Milky Way. The view above us may seem still at first, but it is filled with motion. Earth turning, the moon orbiting, planets circling the sun, stars moving through the galaxy, and light crossing distances too large to picture all at once. For thousands of years, those distant lights have guided travelers, shaped calendars, inspired stories, and opened some of the deepest questions in science. For now, let those distant lights remain where they are, steady and calm above the turning Earth. Let the thought of them settle gently, like stars reflected on dark water. Sleep well. Good night.